Imagine a student preparing for a major exam. They find a practice test and study it relentlessly, memorizing every single question, every tiny detail. But when exam day arrives, they completely fail. Why? Because they didn't actually learn the underlying concepts. They only learned how to pass that specific practice test. When we train computer programs to recognize patterns in data, they often fall into the exact same trap. Instead of learning broad rules, they just memorize the specific dataset we hand them. One common type of program, called a decision tree, is notorious for this. It acts just like our overachieving student, getting easily distracted by every weird, irrelevant quirk or outlier in the data it studies. By hyper-focusing on the practice material, the tree creates rules that are incredibly fragile. When it faces the real world, its predictions fall apart. In machine learning, we call this flaw overfitting. This scatter plot shows exactly what overfitting looks like. The program is trying to separate two categories of data, say red circles and blue squares. But instead of drawing a highly simple logical division, it draws a complex boundary line that zigzags all over the map. It tries so hard to be perfect that it twists itself into knots, creating tiny decision islands just to capture a single, highly unusual red circle sitting in a sea of blue squares. Let's give this model a test with 60 fresh data points. Because it memorized the weird quirks of the old data, 11 of these new dots fall on the wrong side of the boundary line and fail. Relying on a single, hyper-focused model creates high variance, meaning its accuracy swings wildly depending on the data. We need a strategy to forcibly stop the computer from overthinking. To fix this, let's go back to our practice test. Imagine a master test with 1,000 questions. Instead of handing the whole thing to our student, we are going to copy it using a rather bizarre method. We draw one random question from the master pile, photocopy it, and then, critically, we put the original question right back into the master pile before drawing again. We repeat this 1,000 times. Because we always put the original back, the odds get a bit weird. Some questions get drawn and copied twice, or even 3 times. But that also means other questions get skipped entirely. If you run the math on this setup, on average, only about 63% of the original, unique questions make it into this new randomized packet. The rest of the packet is just duplicates. This specific random copying process is called bootstrapping. By hiding some of the data and repeating other parts, we force a model to learn from a slightly distorted, generalized version of the truth, making it impossible to memorize exact details. But we've created an obvious problem. If you hand a student a practice test missing 37% of the material, they are going to have massive blind spots. We solve this with sheer numbers. We repeat the bootstrapping process over and over until we have 50 different highly randomized practice tests. We hand these 50 distinct tests to 50 different computer models. Each model studies its own flawed, incomplete packet, but collectively as a group, they see every single piece of data we have. When it's time to take the real exam with new data, we don't rely on just one program. We have all 50 models vote, and whatever the majority chooses becomes the final answer. This teamwork is known as aggregating. In the world of data science, we call this kind of voting group an ensemble. Because they all studied slightly different material, the consensus of the ensemble overrides the bizarre blind spots of any single model. When you put these two ideas together, bootstrapping the data and aggregating the votes, you get the strategy known simply as bagging. On our test data plot, the single tree gets 11 predictions wrong out of 60. The bagging ensemble drops errors to 6. It cures overthinking, replacing chaotic, jagged islands with a smooth, curving boundary line, reflecting actual patterns rather than memorizing exceptions. This reduces the variance that made our first models so unstable. By crowdsourcing the problem, we get a reliable logic that works consistently across any new data it encounters. This approach also makes training much faster. Because those 50 models are studying completely independently, their training happens in parallel across multiple computer processors at the exact same time. If you are dealing with truly massive amounts of information, you can set each sample to be just a small fraction of the original pile. This means no single computer ever has to load all that data into its memory at once. By simply copying a practice test randomly and letting a team vote on the answers, we've created a system that is accurate, fast, and ready to handle the largest datasets on Earth.